Okay, let's talk about something you're feeling right now. Every single second of every day. It's what keeps your feet planted on the ground and holds entire galaxies together. I'm talking, of course, about gravity. But what if everything we thought we knew about it is wrong? What if the most familiar force in the universe isn't really a force at all? I mean, what if gravity is just an illusion, a side effect of something way deeper, something stranger happening down at the quantum level? That is the absolutely wild idea we're going to unpack today. And trust me, it's a theory that could completely rewrite our most basic understanding of reality itself. So, before we can really dive into this new idea, we gotta go back. We have to understand the giants of physics who got us here in the first place. For centuries, really, our view of gravity has been totally shaped by two names you definitely know: Newton and Einstein. Newton, right, he gave us the first real mathematical handle on this thing. He saw it as this universal, kind of mysterious force, a pull between any two objects with mass. And it acted instantly, right, across the emptiness of space. But then Einstein shows up and just completely flips the script. He said, nope, gravity isn't a pull at all. Einstein's huge breakthrough was realizing that gravity is actually geometry. Think about it like this. Massive things, like our sun, they don't pull on the Earth. They literally bend and warp the fabric of space-time around them, kind of like a bowling ball on a trampoline. So planets like ours, they aren't being pulled. They're just following the straightest possible path through this new curved landscape. It's this beautiful cosmic dance. Mass tells space-time how to curve, and that curved space-time tells matter how to move. And look, Einstein's theory of general relativity is an absolute triumph. I mean, it predicts black holes, gravitational waves, the orbits of planets, all with just stunning accuracy. But when astronomers started pointing their telescopes at entire galaxies, they ran into a massive problem. Einstein's equations just weren't adding up. You can see the problem right here on this chart. It's a huge discrepancy. See that bar on the left? That's the rotation speed we'd predict based on all the stuff we can actually see, stars, gas, dust. But the bar on the right? That's what we actually observe. The stars on the edges of galaxies are just whipping around at these incredible speeds, way too fast. It's like there's some unseen mass, some extra gravitational grip holding them in place. And that brings us to the mainstream solution, the one you've probably heard of. To explain all that extra gravity, physicists came up with the idea of dark matter. It's this mysterious, totally invisible substance that doesn't interact with light at all, but supposedly makes up a staggering 85% of all the matter in the entire universe. But this is where our story takes a really sharp turn. What if we've got it all wrong? What if there isn't any missing matter? What if the problem isn't the stuff in the universe, but the laws of gravity themselves? And that is the starting point for a truly radical alternative. Yeah, this leads us to a completely different picture, one where gravity isn't fundamental at all. Instead, it just emerges from the laws of thermodynamics and information. The theory is called entropic gravity, and the core idea is that gravity is a lot like temperature or pressure. Think about it. A single atom doesn't have a temperature, right? But when you get trillions of them buzzing around together, their collective motion emerges as the sensation we call heat. Well, entropic gravity says gravity is the same kind of thing. It's not a basic force, but an emergent effect that arises from the quantum information of space-time itself. And look, this isn't just some wild idea somebody cooked up overnight. It's actually built on decades of work from some serious heavy hitters. Back in the 70s, you had Bekenstein and Hawking finding this deep, deep link between black holes and thermodynamics. Then, in '95, a physicist named Ted Jacobson actually showed you could derive Einstein's famous equations just from simple thermodynamic principles. It all kind of came to a head in 2009 when Eric Verlinde pulled all these ideas together into what we now call the theory of entropic gravity. Okay, so any new theory is only as good as its predictions, right? And this is where entropic gravity and a closely related theory called MOND, which stands for modified Newtonian dynamics, do something remarkable. They don't just explain those weird galaxy rotations after the fact. No, they predict them with just breathtaking precision. Okay, take a look at this plot. This is called the radial acceleration relation, or RAR for short. It's a huge piece of evidence. So on the bottom axis, you've got the gravity you'd expect to see just from the visible matter in a galaxy. Then on the side axis, you have the gravity that we actually observe. And each one of those little blue dots, that's a real galaxy. The incredible part is that they all fall on this nearly perfect line. It means you can perfectly predict a galaxy's real gravity just from the matter you can see. No dark matter needed. And here's the really crucial point. This super tight relationship is not what you'd expect in the standard model of cosmology, the one with dark matter. In that model, galaxy formation is supposed to be this chaotic, messy process. So getting such a clean, perfect relationship would be, as one physicist put it, bizarre, perhaps even inexplicable. But for these alternative theories, it's a direct core prediction. And the evidence just keeps piling up. Scientists used a totally different method to check this. It's called weak gravitational lensing, where they measure how the gravity from galaxies literally bends the light from objects sitting behind them. And just look at this plot. The relationship holds perfectly, even way out at these incredibly low accelerations where the standard dark matter models predict it should start to fall apart. So case closed, right? This new theory wins? Well, not even close. For all of its stunning success with individual galaxies, this idea runs into some pretty serious roadblocks when you look at both bigger and smaller scales. It really boils down to two major problems. First, when you look at huge clusters of galaxies, the theory helps, but it still doesn't quite get rid of the need for all the dark matter. There's still something missing. But the second problem is much more serious, and it's right here in our own backyard. The version of the theory that works so perfectly for galaxies, it makes the wrong predictions for the orbits of the planets in our solar system. And we're not talking a small error. The disagreement with data we got from the Cassini probe is measured at 9 sigma. In physics, that's a statistical way of saying it is so unlikely to be a random fluke that it's basically considered a fatal contradiction. So this major conflict set the stage for what was supposed to be the ultimate test, a definitive experiment, a tiebreaker designed to finally pit the standard model against this alternative theory in a direct, high-stakes showdown. And this brings us to what's called the wide binary test. The idea is really clever. You look at pairs of stars that are orbiting each other really far apart and very slowly. Their acceleration is so low that they should be the perfect place to see these modified gravity effects. But in what scientists themselves are calling an ugly situation, two different teams analyzed the exact same data and came to the complete opposite conclusion. One team found the stars behave exactly like Newton and Einstein said they should. The other team found a clear 5 sigma detection of the exact effect these alternative theories predict. It's a mess. So, why the huge disagreement? Well, it turns out this analysis is just incredibly difficult. You have to worry about unseen third stars messing with the orbits, you have to account for complex orbital shapes, and you even have to filter out stars that just look like they're close together, but are actually miles apart. Basically, different teams use different methods for cleaning up the data and handling all these potential errors, and that's leading to completely different answers. The ultimate test has, for now at least, only made the mystery even deeper. Which kind of leaves us right back where we started, staring down one of the most profound questions in all of physics. Is gravity a fundamental ingredient of our reality, something woven into the very fabric of space-time? Or is it more like the concept of wetness? You know, wetness isn't a property of a single water molecule, it's a collective behavior that only emerges when you get trillions of them together. Is gravity like that? We honestly don't have the answer yet, but the search for it is pushing the absolute boundaries of what we even think we know about reality itself.